Maybe you don't know what complex numbers are, or maybe you just need a refresher. Well, you've come to the right place. This is complex numbers explained by an engineer. So I'm going to start with something familiar. These are the axes of a graph. We all know them, pretty standard. We normally call them x and y. If we want to represent a point, we can do it using this kind of bracket notation. So if we go along 2 in the x-axis and 1 in the y-axis, we have a point here. We can call this point 2, 1. Pretty normal so far. We can also do this in the vector notation, which just looks like this, which is just 2, 1. Pretty simple. But the bracket notation is a little bit cumbersome. I mean, you've got to draw all those brackets, it's kind of annoying, and you're not really sure, or it's not obvious, how to add and multiply numbers. What if we could represent this information in a single number? So this time I'm going to call this axis the real axis and this axis the imaginary axis, although it doesn't really matter. For ease, I could call them x and z. So we have our point somewhere here. Now we want to call this something so we can represent it in a single number. We'll call it z. Well, obviously there are two parts to this z. There's the horizontal part and there's the vertical part. So we basically need a way of getting a number from the real axis to the imaginary axis. And that number, if you think about it, will represent the horizontal or the vertical component of z. So z is going to be equal to 2 plus I. So we've gone along 2 and we've gone up the 1. 2 plus I. That's pretty simple. So what is this I? Well, we know that 1 times by I is equal to I. Now you might think there's nothing crazy about that, and there isn't. So all that's going to do is take us from this point to this point. So what is that? Well, we've just gone 90 degrees anti-clockwise. So we know, geometrically speaking, that timesing by I is equivalent to a 90-degree anti-clockwise rotation. That kind of makes sense so far. But what if we do I times by I? Well, obviously that gets us I squared, but where does that leave us on the graph? Well, if we've gone from 1, we get to I by timesing there, and then we've got I, and then we're going to times by I again, and that gets us over on this side of the imaginary axis. So here we're at 1, then we're at I, and now we're down to minus 1. That's pretty crazy. So that means that I squared is equal to minus 1. Or to put it another way, I is equal to the square root of minus 1. So if you're wondering where that's come from, that's where it's come from. So we can carry on and we can do minus 1 times I, and that's just going to take us down to minus I. Then if we have minus I times I again, that's going to take us up to 1. I hope you can see that. So if we draw out our axis again, and we pick a point, we can draw a line from this point to the origin. Okay, that's pretty standard. So what do we know about this line? How can we represent this line? Well, we know that we can represent it in the way we did over here, and let's just call that x plus iy. We can also say it's x plus yi. Either one is correct. But there's also another way we could give this line. This line is a certain length, and it's a certain rotation from the x-axis, so the positive x-axis. So if we call this angle theta, we can call this length r, although we could really use any letter. Now, this gives us different ways of representing complex numbers. So if you imagine we have z, algebraically we can just write out x plus y I. This is the Cartesian form. But we can also write it out with this and this, the magnitude and angle. So we call this angle the argument, it is r, and then the angle sign, theta. And that just represents the same information. So if you look at this line, you can imagine drawing a line like this down here at 90 degrees to the axis. And what that would do is get us a right angle triangle. So I hope you all remember your trigonometry. So we've got the hypotenuse, the opposite, which is the opposite to the angle, and the adjacent. Now, we need a way of going from this x plus yi form to this magnitude and direction form. How can we do that? Well, we use this triangle. So, if you remember from mathematics, we have SOHCAHTOA. You don't have to remember it in this way, this is just the way I was taught to remember it. So we want to find the relationship between the angle and the numbers that we know. And if you think about it, O in this case is equal to this y, and A is equal to this x. So what we can do is simply write the tangent of theta is equal to O of A, which is equal to y divided by x. That makes sense, but we actually want the angle, so we can write this as the angle theta is equal to the arctangent of y over x. Now remember that arctan simply means the inverse tangent, nothing else. It's just that if you write this with the little symbol up in the corner, it's quite easy to get mixed up or make a mistake. So I like to write the arctan out. So what else do we know? Well, we have Pythagoras Theorem. We know that h squared is equal to o squared plus a squared. Pretty standard stuff. So we can use this to our advantage and say that this r is equal to the y squared plus the x squared inside a square root. Nothing crazy there. And using these two formulae, we can go from this x plus yi to this theta and r. So we call this form the polar form. And those are the two main forms that you generally see complex numbers written in. But we also have two more forms that we've got to talk about. So we know the SOHCAHTOA rules. We can write them out. So looking at this triangle, so keep in mind this is x, this is y. We can say that the sine of theta is equal to, and it's O divided by h, which is y divided by r. And we know that the cosine of theta is equal to a divided by h, which is x divided by r. So if we rearrange this, we can find an expression for the x and for the y. And with these two formulae, we can go from this r and theta to the x and the y. And therefore we can say x plus yi and get the Cartesian form. But there's something else that these forms will tell us. We can write down z is equal to x plus iy, and we can substitute this r cosine theta and r sine theta. So what does that give us? R cosine theta plus I r sine theta. And we can factorize the r. And that gives us another form of the complex number z. Now, there's something which maybe you'll not be familiar with called Euler's theorem, otherwise known as Euler's theorem, depending on how you pronounce it. So we know that e, which is the exponential number, times I of theta, the power of I of theta, is equal to cosine theta plus I sine theta. Now, that may seem pretty strange, and it is. The way you derive that is by using some kind of complex Maclaurin series, which I don't care to do. But nevertheless, that's the correct result. So what can we say about this? Well, if you substitute this cosine plus I sine into this formula, we have another form for z. So we can say that z is equal to r times e to the I theta. And we call this exponential form. This is all pretty strange. So what is this exponential form? What is this telling us? What is this sine and cosine form telling us? Well, let's think about what sine and cosine actually look like. So I'm going to start by drawing sine. If you are in any kind of high school maths exam, you should be able to sketch sine and cosine. I'll give you my way of doing that. Sort of a line up here, a line through there, line through there. Now, you've got these sort of little sections of line. All you have to do is convincingly join them up. I'm not going to win any awards for neatness anytime soon, but you get the general idea. Now, we know that this function basically goes on forever, and what's more, it repeats on this point here. Now, in degrees, this is 360 degrees, but in radians, it is 2 pi radians. What does this mean for our function? Well, if you take the cosine 2 pi along the x-axis, or back along the x-axis, it'll have the same value, and the same is true of the sine. So if you look at any 2 points, maybe this point and this point, they're going to be the same as long as the difference is 2 pi radians, or 360 degrees. What does this mean for our complex number? Well, if you think about it, it makes sense. So we have our complex number there, that's at some angle. So if you go around 360 degrees, how's the angle going to change? It's not. Pretty simple, pretty straightforward. However, it's not just 360 degrees, it's any multiple of 360 degrees. So just using the radian form, we can say that this guy down here is equal to this. So r times e to the I pi, or to the I theta, plus 2k pi. However, this k has got to be a number like 0, 1, 2, could also be -1, -2, some integer, basically. We say in mathematics that k is a member of the integer group. Pretty standard stuff. There's also 2 more things that you need to know about complex numbers. We have what's called the modulus function, which is just written like 2 lines that go around the number. So if you take the modulus of z, all it does is give you this r, which is equal to x squared plus y squared in a square root. Pretty simple stuff. There's also the argument, which is normally just written as arg and then some brackets, which is just equal to the inverse tangent of y divided by x. So why do we call this theta the argument? Well, it's just another name for it. It just means angle. You'll find that engineers sometimes use j, or sometimes, very occasionally, k instead of I. It just means the same thing until you get onto some 3D vector geometry and all that jazz, which I don't really have time to get into. If you do have any questions or comments or mistakes that I've made, suggestions, put them down in the comments below. Thank you very much for listening.